Let's now briefly review some of the methods used to study big history. The task is challenging because of the wide range of scales involved, the diversity of units of analysis, the blurred nature of transitions, and the limited availability of detailed quantitative data. Often there is little quantitative data because many of these processes did not leave behind physical records that can be measured directly, such as fossils or other durable traces. The evolutionary processes also occur over broad spatial and temporal scales, making it difficult to assign precise times to specific events. In addition, they cannot be reproduced in controlled experiments. As a result, models are usually not detailed enough to fully capture these processes. A general approach to big history and related frameworks is to draw on whatever evidence is available, integrating perspectives from many angles and treating results as proof of principle with varying weights of evidence. This often involves moving across levels of abstraction in physics and systems thinking, including nonlinear dynamics, bifurcations, energy flows, and processes of reorganization, along with rough estimates and approximations, AP. Multiple perspectives are used to track changes in several coupled characteristics, e.g., EIEIO-style descriptions of complexity, requirements, and resulting products, as well as to identify scaling laws and structural regularities. These are complemented by analogies and recurring patterns drawn from physical processes such as bonding and phase transitions, network structures, growth curves, including population dynamics, feedback-driven system dynamics, and rule-based system comparisons. Finally, event rate analysis provides another lens, though it remains limited by simplifying assumptions. It draws on physics, historical data, and notions of acceleration to assess whether observed patterns reflect real temporal trends or artifacts of modeling choices. To determine the plausibility that total system energy has increased in a manner similar to complexity, estimates were made for a potential site of life's origin and compared with current global energy use. A somewhat larger growth factor is plausible, as energy use per unit tends to increase over time. This approach can be extended by estimating system energy at other scales, although doing so becomes more difficult due to challenges in defining appropriate system boundaries. One way to compare independent framework proposals is to define a common set of criteria and evaluate each framework against them. These criteria may include links to established disciplines, the degree of integration with theoretical and explanatory models, and the potential for extension into greater detail and future developments. Some transitions can be empirically modeled by tracking the rate of key events. Then a physical analogy might describe their main features. For the shift from hunter-gatherer societies to agriculture, rising population density increased competition for land, with hunter-gatherers requiring much more land than farmers. In early farming communities, larger families were beneficial for labor, further increasing population pressure and reinforcing a feedback loop that supported agricultural settlement. This process can be compared to a phase transition, like a gas condensing into a liquid under pressure, with hunter-gatherers as a gas-like state and agricultural societies as a liquid-like state. Event rate analysis shows that the smaller steps within a larger transition might start slow, speed up, and then slow again. This is a standard pattern seen in commerce and maturing innovations. This shows the transition from hunter-gathering to agriculture occurred over a long period of about 10,000 years, with the fastest rate of innovations at about 9,000 years ago. Another approach is to apply many different perspectives to see if they provide a consistent interpretation of the evidence. This will now be applied to the event rate analysis of major big history events. Many independent analyses have used a variety of number of events from the big history narrative. However, in looking at the organization of traditional disciplines suggests a broad division of evolution into three parts, which is also similar to Jantz's analysis. The weight of evidence combines many inconclusive separate pieces of evidence from a series of perspectives to form a set that is self-consistent. Theory. In the 1970s, Eigen proposed that evolution may follow a singularity-like pattern. A related idea is that small changes in collective learning dynamics can shift growth from exponential to hyperbolic behavior, potentially approaching a singularity. This is sometimes compared to cascade to chaos behavior in fractal systems, where incremental changes produce strongly nonlinear outcomes. Empirical observations. Event rates of system change often appear to follow singular patterns. This is similar to the wider pattern seen in structured educational sequences in fields such as biology, anthropology, and history. Real systems. In empirical data, global population growth exhibited an apparent singular trend up to around 1970. Similar nested transitions have also been suggested in the historical rate of physics discoveries. Estimations might be based on certain assumptions such as planet needs to be at distance for liquid water. Planet needs to be massive enough to not let atmosphere escape. Animal size should be that falls are not catastrophic. Electron in atom balances uncertainty and attraction to proton. Just as Darwin's theory of evolution is continually debated, refined, and extended in light of new findings and interpretations, our understanding of big history will likewise continue to evolve. As new data, methods, and interdisciplinary perspectives emerge, key narratives and explanatory frameworks are likely to be revised, expanded, or even replaced. This ongoing process of refinement reflects the complexity of the subject itself, where multiple scales of time and organization are interconnected and continually reinterpreted. Here are some open access papers that were used to construct this presentation.